Just to give some background on where I'm coming from this, my work essentially breaks into 3 different parts. So one part is I develop algorithms for probabilistic inference. The second part of my job is I incorporate those algorithms into a probabilistic programming language called infer.net. And then the third part is I apply probabilistic programming and infer.net to various products in Microsoft. The most recent thing that I'm working on is upgrading TrueScale to have a better generative model. Now, since we developed infer.net 15 years ago, there's actually been a huge explosion in interest in machine learning languages, not just in probabilistic programming languages, but also in languages for deep learning and so on, and other types of machine learning. And if you look around, you basically see that every major tech company and university has their own machine learning language these days, maybe even more than one. And the reason why they're doing this is basically because machine learning algorithms are complex, and these languages essentially simplify the implementation of machine learning algorithms. Now, the situation we're in right now is that these machine learning languages are sort of like domain-specific languages in the sense that they simplify one type of algorithm. And if you want to use another type of machine learning algorithm, you have to use another type of language. And the way I see things moving in the future is that essentially all languages will be able to support the same sort of operations. They'll be able to support the same sort of algorithms underneath. They'll just have different surface syntax, which is the way normal programming languages are, right? They essentially can do the same things. They just have different surface syntax. So the way I see the future going is that we want general purpose machine learning languages so that they can implement any machine learning algorithm in it. And so that then leads to the question of, well, what technology would enable such general purpose languages? What would the back end of such a general purpose language look like? And I will argue that it's message passing. I think we can actually draw a lot of inspiration from automatic differentiation, in fact, because a lot of the machine learning languages out there use automatic differentiation as a component. It's a very common component, very successful component. However, I think it's not enough. It's in a sense too low level. So at one level at the high level you've got machine learning algorithms like black box variational inference or Hamiltonian Monte Carlo, and then at the lower level you have automatic differentiation. I think what we need are tools that sit in between, and that's where I think message passing fits in. So the overview of the talk is that I'm going to first give an overview of I'm going to give an introduction to what automatic differentiation is and how it works. And even if you know what automatic differentiation is, I think you'll find this interesting because I view it in a different way than many other papers explain it. And that view is that different view is actually useful in terms of connecting it to message passing. And what I will emphasize is sort of what I consider a flaw in automatic differentiation, which is that it lacks the concept of approximation. And I think in order to have a general purpose machine learning language, you really need a concept of approximation, and it has to be native to the language because many machine learning algorithms use approximation, and I'll explain that more. I'll also talk about how you can do a source-to-source transformation for automatic differentiation, and you can extend that same source-to-source transformation for message passing. Okay, so automatic differentiation. Now, one thing I've noticed is that there's actually some confusion out there. Some people, when they use the term automatic differentiation, they just mean any method for computing a derivative automatically. That's actually not what I mean in this talk. I'm actually talking about a very specific algorithm for computing the derivative. And that algorithm tends to be called in the literature algorithmic differentiation. So if I want to be super precise, I would say algorithmic differentiation. However, I'm so used to using the word AutoDiff and automatic differentiation, I probably won't be that precise, but that is what I mean. The book that you should all read if you're interested in automatic differentiation and algorithmic differentiation is one called Evaluating Derivatives by Greerank and Walther. I think if you're interested in machine learning languages in general, or basically how they work, how they're implemented, or if you want to build your own machine learning language, you should definitely read this book, mainly because even though it doesn't talk about machine learning or probabilities at all, the ideas are very relevant to any machine learning language because essentially you can think of AD as a blueprint for how for how a machine learning language would work, basically how you would transform an input specification into a numerical algorithm at the end. And the book has a lot of great ideas that go beyond AD. Okay, so the first step to understanding AD is this idea that programs are the new formulas. So in school, we learned how to take derivatives of a formula, and AD goes much further than that. So the basic idea is that by using a program to represent a mathematical function instead of a formula, not only is it more compact, not only is the input more compact, but the output is also more compact. And in fact, the input and the output are of roughly the same size when you take the derivative, which is not true for formulas. But even when I talk about programs, I don't mean something that you just execute. I don't mean like a black box that you run. What I mean is something that's more like an expression language, which just happens to have rich constructs like while loops and recursion and so on. So essentially, it's a kind of formula, but a richer formula. So we're going to be analyzing the syntax of the programs and not just running them. And then another important distinction from regular programs is that all the numbers in these programs are assumed to have infinite precision, and that will allow sort of algebraic manipulations to happen, and without worrying about the consequences, which you would have to worry about in a real programming language. So in a sense, these programs are kind of like idealized programming languages, which if you think about it, that is actually what the input to every machine learning language is. It's an idealized version of a programming language, not the real programming language. Okay, so to illustrate my point about programs versus formulas, if you think about what the formula would be for multiplying a bunch of numbers, it's fairly compact. So you can write it using this pi I notation, or you can just write it out as x1 times x2 and so on, and that's fairly compact. It's just linear in the number of variables you're multiplying. But if you think about what would happen if you took the derivative of that expression, it actually gets a lot more complicated. So in this case, I can write it compactly this way, but you can already see it's bigger than the original input. And if I wasn't using this pi and sigma notation, it would be much larger. If I actually unrolled it, it would actually be quadratic in size compared to the input formula. And that doesn't happen with programs. So to illustrate what happens with programs, here I've written down what the program would be, or one possible program for multiplying an array of numbers, right? So all this does is it multiplies x1 to xn. And I'm doing the multiplication in a bit of a funny way. I'm using this accumulator array, this ci, which is the product of all x's up to I. And there's a good reason for me writing it in this funny way, which I'll explain later. But the important thing to realize is that you can convert this program in a way that I'll soon explain to get a derivative program. And this derivative program computes that formula for the derivative, but does it in the same size program and roughly the same amount of work. So it's the same amount of computation is being done. So it does not blow up quadratically the way the formula did. And that's generally true for derivatives, although I won't prove that. In fact, it's not even obvious from the program that actually implements that formula, right? Unless you understand how the program is derived. Okay, so the way AD the way I'm going to explain AD is that it works in two phases. So the first phase is an execution phase, where you go through the original program and you replace every operation that was done there with a linear operation. So you linearize the program essentially, but only the mathematical operations, not the control flow. And then secondly, you then perform this accumulation phase, which essentially collects all the linear coefficients, all the coefficients of these linear operations. And that's how you get your gradient. So let's start with the execution phase. So I'll start with a very simple concrete example. You can interpret this as a program or as a formula, right? So x times y plus y times z. And a helpful way to visualize what's going on in AD is to look at these computation graphs, which represent the programs, or in this case, the formula. So the way you read this computation graph is you have variables at the top, and then you have temporary quantities in the middle, and I've sort of labeled each one with the operation used to get it. Hopefully that should be intuitive. And what the execution phase does is it linearizes all these operations. So the graph is going to have exactly the same shape as it did, but any place where you combine two things in a nonlinear way is now going to be a linear combination. So instead of x times y, you're now going to have dx times y plus x times dy. Now the way you read the graph on the right is that these expressions I put on the edges are scale factors. So as you pass through along one of these edges, you just multiply by the number that's on that edge. And the operations that are going to be in the intermediate nodes are always going to be plus, because it's always linear. And when I say linear, what I mean is it's linear in the input arguments, the things at the top. So the original inputs x, y, and z, it's not meant to be linear with respect to those. It's linear with respect to the d's. Now, one thing to keep in mind is that the things on the edges are now regarded as constants. So when I say that it's linear, I'm saying that y and x are now considered fixed, and it's just a function of dx, dy, and dz. So you can derive the expression at the top sort of by hand, and I'm just showing what the computation graph would look like. Okay, so that's the idea of what the execution phase does. It just makes that linearization. Then the next phase is the accumulation phase, where you use this linearized program to get the gradient. So here's the same graph we had in the previous slide, and the formula that I've written above is not really in the right form to be the gradient. So the gradient is meant to be a vector with 3 entries. The first entry is the coefficient of dx, the second is the coefficient of dy, and the third is the coefficient of dz. Right? Now, that's what I've written on the side here. Now you could work out what those coefficients are by essentially performing algebraic manipulations on that formula. Right? You could do computer algebra. However, that's not how AD works. It doesn't do computer algebra. So what it actually does is it performs a algorithm on this graph. It performs a dynamic programming algorithm on the graph where it collects values upward. And so one way to think about that is that to get the coefficient of dx, right, I can sort of read it off the graph because I can see that there's a single path from dx to the output, and along that path I multiply by y, and then I multiply by 1. And so just by seeing that, I know that the coefficient of dx is 1 times y. And similarly for z, I see that there's one path, and I multiply 1 times y, and that's the coefficient of dz. So I can sort of read the gradient off of this graph. Now for the dy, it's a bit more complicated because there's 2 paths to get to the output. And all you do in that case is you just add the results from both paths, because it's a linear function, so of course you would always add. So along one path we get 1 times x, and then the other path we get 1 times z, and then indeed that's the coefficient of dy in the gradient. So here's what would happen in a sort of more general case. So here I have the same graph structure, but I've just generalized all the coefficients to be arbitrary. I don't have those ones there, and that just corresponds to a composition of linear functions, right? A times x plus b times y gets composed with another linear function. And what we're trying to do here is we're trying to work out what is the coefficient of x in this linear function, what's the coefficient of y, and what's the coefficient of z, right? And we can do that by following paths in the graph. So in the case of the coefficient of x, as I say, you can sort of pass a message up from the result. We're going to do this backward message passing algorithm now. So we pass this message up, which is just going to be e, up to that intermediate node, and then we're going to multiply by a, and we get e times a, and that's the message that arrives at x, and that's its coefficient in this linear function. So in this case, I'm not really talking about derivatives anymore. I'm just saying what is the coefficient of the input in this linear function, right? In the case of z, it's the same thing. We pass up f, and then that gets multiplied by d, and then what arrives at z is f times d, which is its coefficient. And in the case of y, we can actually reuse a lot of the work. So a message has already arrived at this intermediate node on the left, and all we need to do is multiply that again by b, and then e times b arrives at y, and then from the other direction, f times c arrives at y, and whenever 2 of these messages arrive at a variable, you add them together. And that's how you get the coefficient of y. So essentially, you can read it off of the graph by following paths. And so this is sort of the key to my interpretation of automatic differentiation, is that this reverse accumulation process is literally just a dynamic programming algorithm. It's one specific kind of dynamic programming algorithm. And what this algorithm is computing is it's computing every backward message in this graph is the sum over all paths of this linear function to the output, right? So you take all possible paths that this node has to the output, and you sum up these linear functions. And you can show basically by induction that this always computes the exact coefficients going up the graph. Okay. Now another interesting aspect of AD is that you can do it via a source-to-source translation. So far I've been talking about computation graphs, and a lot of the older techniques, older tools for AD, they would actually build these computation graphs, and they would actually do the dynamic programming on the computation graphs. So TensorFlow comes to mind, which I would call the old style of doing things. And so the newer approach, which actually happened way before TensorFlow, but is called source-to-source method. And what you do there is you take your original input program and you actually make a derivative program out of it, like the one that I showed earlier. So in fact, I'll talk about how you derive that derivative program that I showed earlier. So here I'm going back to the example of multiplying an array of numbers, right? And so the key step here is that, as I say, we want to linearize every operation in this program. Now, there's only one nonlinear operation, and that's that multiplication between ci minus 1 and xi. And so, again, I like to think in terms of graphs. So let's draw the little graph that corresponds to that nonlinear operation. And what should it turn into? It should turn into a linear function of its two inputs. And so what I'm going to do is I'm going to rename the two inputs to have d in the front of them. And then as the coefficient on that operation, I put the partial derivative of that operation, which in this case is xi and ci minus 1. And then all you do to get the derivative program is you rename all the variables that have d on the front, and you just replace the operations with their linear equivalent. So that's it. That's how I got that derivative program. I'm not going to prove that's correct. You'll have to take my word for it that works for any program. Now, in the literature, on AD, when you look up sort of how people derive these derivative programs or tangent programs, they will often interleave the operations between the input program and the derivative program, because after all, I need to compute CI before I can use it in the derivative program, right? So this program is referring to variables that were in the original program. So in practice, if you wanted to actually compute DCN, I would have to either first compute this program and then compute that program, or more efficiently, interleave the operations of this program and that program. However, I find it confusing to have the operations interleaved. So actually, I think it's actually a lot more clear to just think of it as two separate programs, one of which you just happen to run before the other one.
Is that why you have to write it in the funny way with the CI? With C being an array, so you remember all those intermediates?
Correct. That's one of the reasons, yes.
And if you just happen to not write it that way, then you'd be somehow stuffed?
Yes, exactly.
Okay.
Yes.
How would you know that you were stuffed? In other words, what property of the original program makes it?
You're anticipating a slide 3 from now.
Okay, cool.
Okay. So that was the first phase of AD. The second phase is this accumulation phase, and that can also be done via source-to-source transformation. So here, what we're going to do is I'm going to take that derivative program that I had on the previous slide. I'm going to turn it into a gradient program, which is the program that computes the gradient with respect to all the x's on the input, right? So the output is going to be an array of gradients. And so the way this transformation works is, remember, it's implementing this reverse dynamic programming, right? So it has to work in reverse. All of the operations in the original program have to be visited in reverse. So what's going to happen is we're going to go through each of the lines of the derivative program in reverse order and turn it into a line in the gradient program. So starting with the last line, we have this return statement. And by definition, when you just have a return statement, you set the backward message to 1. And that's basically like saying the bottom node in the graph, what is his incoming message? Well, that's just 1. Next, we have a for loop. And since we're reversing all control flow, we just reverse the direction of that for loop. So that's easy. Next, we have this statement. And the way this transforms is again, you keep the graph in mind. That's how I always like to think about it. So this is the graph for that linear operation. And remember, we're receiving this message in the bottom, which I'm calling DCBI. So in this new program, I just added the letter B to everything. Those are the new variables. And having received that message in the bottom, what's the message to the left? Well, all you do is you multiply it by xi, right? So you end up getting 2 lines of code. So one line of code computes that message to the left. DCBI minus 1 is equal to that times xi. And then you have a message to the right. So it turns into two lines of code on the right. Hopefully that's clear. It's clear once you see the graph, I should say. And then finally, we have the first statement of the program, which is sort of a trivial linear operation. And all you do there is you're essentially swapping left and right. Okay. And that's how you get the gradient program in this example. And hopefully that shows why it's a correct gradient program. Now, if I just gave you that program, you'd have to scratch your head. Is that actually computing the right gradient? But if you drive it this way, it's clear that it is. So what does this look like in the more general case? So if my original program has a line like c equals fxy, which is some nonlinear operation, then when you do the first phase, the execution phase, you're going to turn that into a linear line of code. So you just change the c to a dc, and then that first coefficient df1 is the partial derivative of f with respect to its first argument, which we're now going to regard as a constant, which is known, and then we're going to multiply it by dx. And then in the next phase, the accumulation phase, we think about that linear function in terms of this graph, and we say, okay, what are the messages I need to send? And I need to send two messages, one to dx and one to dy, and so you get these two lines of code sending those messages. Hopefully that's clear. And that's all you need. Those are the only rules you need to know for this simple example, because I made the example simple, as Simon pointed out. So how did I make it simple? So the way I made it simple is I made sure there was no fan out. So in other words, if a variable is there was no variable that was read multiple times. If you look at that program, every variable was used exactly once. And that's a property of the fact that I use this accumulator array of c's instead of having one c that I repeatedly updated. And because there's no fan out, we never needed to add messages together in the backward pass, right? So, but if a variable is used multiple times, if there is fan out, then we need to have this step where we add together backward messages. Now, in the literature, there are sort of two different ways of dealing with this adding process. So one way is the incremental approach, which is where you create a program that destructively modifies the message into a variable. So every time you visit one of the children of a variable, you sort of destructively increment the message for that variable. And that's the way it's usually presented because it's usually what's more efficient. However, what I'm going to present today is the non-incremental approach. So in the non-incremental approach, all of the child messages are first computed, and then at the very end, they get added. So there actually is no mutation that happens in the output program. It's a mutation-free program. And one benefit of that is actually it's a lot easier to parallelize the non-incremental approach. But an even bigger benefit is that it connects with message passing, and I'll show you why that is. Okay, so here I'm going to give an example of this, how this fan out is handled on a very, very simple input program which has fan out. So here, this is actually the same example I gave earlier, but what I've done is I've named all the different temporaries. So A is now x times y, B is y times z, and so on. And so what I'm going to do is I'm going to transform this input program into a program that does not have fan out. So that's the trick. So fan out is bad, so we just get rid of fan out. And so the rule here is that if a variable is ever used more than, so basically I'm going to transform the program so that on any execution path, a variable is defined once and it's used once. It's never used multiple times. And it turns out you can essentially do that by adding these duplication steps. So what I've done in the case of y, which is used multiple times, is I've added this new statement which duplicates y. And so this dupe operator simply creates a pair of the same value, right? And I'm unpacking that into y1 and y2. So now this program only uses every variable once. It satisfies my constraint. And here you can think of it as being a sort of graph modification. So where I had a node with two children, I now have this duplication operator. And what's interesting about having a variable defined and used once is you can now think of them as edges. And I'll go into more detail about what that actually means, but that's why I call it an edge program, because these variables now have one source and one target, always. Okay, having made that transformation, I can now apply the rules I already gave for getting the gradient program. Everything works nicely, except that I just have to add one extra rule for how do you translate dupe. And the way you translate dupe is super simple. It's just when you receive a message, when you receive messages from your children, you add them together. Okay, so that's how you handle fan out. Now, if I had written my original program without that C array, if I had written it using a mutating accumulator, then there would have to have been a program transformation prior to AD, which essentially removed the fan out. Okay, so essentially that's my whirlwind summary of AutoDiff. Here's a table which summarizes all of the properties of AutoDiff. And I've also included a column for message passing to sort of show you how things are going to change when we go to message passing. So that's why I said that AD uses programs instead of formulas. That's also true for message passing. It has this nice property of exploiting graph structure and sparsity, so does message passing. You can do it via source-to-source transformation, same with message passing. And then there's three properties of AD that I would claim are actually not as good as you might think. So AD, for example, only explores one execution path through the program. So even though there is control flow in the program, what's going to end up happening is you're only going to explore, your derivative is only going to essentially look at the one execution path at your input, at the input you're taking the derivative, right? It doesn't explore alternative execution paths. Whereas it turns out message passing will do that. Another property of AD is that it uses a single forward-backward sweep. So essentially, it runs your program once forward to get all of those coefficients, and then it runs it essentially in reverse to get the gradient, and then it's done, right? But message passing won't always do that. Sometimes it'll require multiple forward-backward sweeps. And then the final and I think worst property of AD is that it's exact. It always computes the exact derivative, at least under this infinite precision assumption. And I'm going to explain why I think that's so bad, basically because machine learning algorithms generally aren't exact. They don't want to be exact. They don't try to be exact. Okay, so now we're getting to the next part of the talk, which is why it's so bad that AutoDiff is exact. And basically, it's because approximations occur all over machine learning. So I'm going to give you a bunch of examples of where approximations appear in machine learning, and they're very important approximations. So one case where it appears all the time is when you're training a model on a big data set. So for example, if you're training a deep network on a large data set, you typically won't compute the exact gradient, right? It's been known for a long time that it's actually much more efficient to compute an approximate gradient. And the way that approximate gradient is typically computed is you'll have some objective function, some training loss, which is a big sum, as you can see on the right. It's some big sum over data points, which is what you're trying to optimize or minimize. And the way you approximate the gradient of that thing is you first replace the sum with some important sampling estimate, right? So you draw some subset of points, and then you reweight it, and that's your approximate sum. And then what you do is you apply AutoDiff to take the exact gradient of that sum, and that gives you your approximate gradient, right? So, but keep in mind the order of steps here. You're approximating your problem, and then you're running exact AD, which you have to do because AD is always exact, right? So that's the only way to get an approximate gradient from AD. Here's another example. So black box variational inference. So in this method, you're trying to approximate the posterior distribution over some variables in a probabilistic program. And the way it typically proceeds is you start by approximating the marginal log likelihood of your model with some lower bound, right? So here I've written the formula that people often use. But then you realize, oh, this lower bound actually can't be computed exactly. So what I'm going to do is I'm going to approximate that lower bound by importance sampling, which is a different use of importance sampling than what we just saw. So it's not. So you could even do mini batching on top of it, which is yet another form of approximation. And then finally, at the end of all that, you compute the exact gradient of the approximation, and then that's how you find your posterior. So same story. Approximation happens, and then you take AutoDiff. So what about tractable models? So something interesting happens in tractable models. So when I say tractable, I mean something like a Markov chain or a generative grammar, a parse tree model or a tree structured Bayesian net, something like that, where you can essentially compute marginals exactly already. So for a Markov chain, you can just use the forward-backward algorithm and get marginals. And what's interesting there is that it's actually been known for a long time that you can use AutoDiff to mechanically derive these summation algorithms, or at least the reverse summation algorithms. So the way this works is if you write a program which does the forward inference computation in a Markov chain, and then you take the derivative of that program, it will give you the backward computation in a Markov chain. Since the derivative program computes the forward program before it computes the derivative, that whole program as a whole is now the forward-backward algorithm in Markov chains. And people have noticed that that's also true for any sort of Bayes network. It's also true for grammar models and parse trees. I'm citing papers where they made this observation. Now, one way to see why that equivalence holds is that the expectations of the posterior are always going to be derivatives of the marginal log likelihood, which you can compute exactly. So if you start with a program for computing the marginal log likelihood and you run AD on it, you must get something which computes posterior expectations, right, in these sort of tractable models. However, I think that's an incomplete explanation. And the reason it's incomplete is because it doesn't capture the fact that AD is not just computing the same answer that the forward-backward algorithm would compute. It's even doing it the same way. So it's actually using the same algorithm for computing the forward-backward updates. And that's because it's not just any old algorithm for computing the gradient. It's this dynamic programming algorithm for computing the gradient. And it just so happens that dynamic programming algorithm for computing the gradient is the same dynamic programming algorithm you would use in a Markov chain or Bayes net or a parse tree. And that's why they're equivalent. So now getting back to approximation, even in these so-called tractable models, when you see how they're used in practice, there's always approximations. So for example, if you're using Markov chains for speech recognition, or you're doing information extraction with conditional random fields, or you're doing parsing of natural language, almost all of these applications make approximations. They don't use the exact algorithms that you'd get out of the AD approach. So for example, in a Markov chain, you typically use a sparse forward-backward algorithm. And in a sparse forward-backward algorithm, you're making approximations in the forward pass, and you're making a different set of approximations in the backward pass. And you cannot derive this via AutoDiff, right? So if I did an approximate forward pass, and then I did AutoDiff, I would then be doing an exact back pass on that approximate forward pass, which I would argue doesn't even make sense. So so you can't get these algorithms through AutoDiff. And you also can't get an algorithm like Viterbi out of AutoDiff, even though Viterbi is a very natural dynamic programming algorithm with essentially the same structure. You can't get it out of AutoDiff because it's the wrong dynamic programming algorithm. Okay, so this essentially is my point, that if we want a substrate for machine learning languages, which is generally usable and allows you to implement a wide variety of algorithms, it should facilitate approximation. It should not be an exact algorithm. And that also implies that the machine learning language itself should have some way for the user to specify what is their goal, what is the thing that they're trying to approximate. In other words, we shouldn't require the user to approximate their problem first. They should say, here's my problem, now go approximate it. And so one type of goal that you might specify is, well, I want to compute the expectation of something, right? As we just saw. Expectations arise a lot. Another example would be, I'm trying to optimize something, or I'm trying to find the solution of a set of equations. And these often will involve some sort of fixed point iteration. So maybe the concept of fixed point iteration should be a native concept as well. And so I would argue that, in fact, looking forward, all of these should be natively supported. Now, I haven't seen any language which does that. This is just sort of an idea that I had. But in fact, in the AD book that I cited earlier, they actually do make a case that it's useful for fixed point iteration to be a native concept in the language. And you might want to check that out. Okay, so on to message passing. So how does message passing generalize AutoDiff? So at that very highest level, the way I would summarize what message passing is it's approximate reasoning about the exponential state space of a program along all of its execution paths. So it's not just following the one execution path that AutoDiff does. And because it's reasoning about an exponential state space, it essentially has to do something approximate, right? So the notion of approximation, I think, is inherent in the general idea of message passing. And what ends up happening is that the way you solve these problems is that you propagate these summaries of the program state in both directions. And the forward messages that you send can depend on the backward messages and vice versa, and that leads to a sort of chicken and egg problem, and usually solve that by iterating to convergence. Now, people here who are familiar with abstract interpretation will say, hey, that's not like abstract interpretation. Indeed it is. In fact, it's very similar to quite a lot of algorithms in computer science. I would say it's kind of an umbrella term for sort of a general category of algorithms in computer science. So things like the Viterbi shortest path algorithms and so on, they can all fit into this framework. Okay, so that was a very abstract. I will give a more concrete example of what message passing is, and then I'll show how to implement it via a program transformation. So the very simple example I'm going to use does not involve any complicated math. It does not involve probabilities, right? So hopefully anyone should understand it. It's just interval constraint propagation. So the idea is that given a program, we want to reason about what is the largest and smallest value that any variable could have in this program under any valid execution of the program. And so the basic idea is we're going to take this program, we're going to interpret all the operations in this program as constraints between their input and their output. And we're going to propagate information forward and backward through this program into conversions. Essentially, we're going to solve the set of constraints through the program. So it's sort of like a constraint solver. So to make it even more concrete, I'm going to look at one specific example, which is to find where does a circle intersect a parabola. And so the problem will be find the point x, y that satisfies this circle constraint and also this parabola constraint. So what we do is we start by encoding this as a program. So what I've done here is I've written a program that sort of names every intermediate variable like it did before. And what I'm doing is here is I'm using an assertion. So one of the constraints is just going to be an assignment y equals x squared. That was the first constraint. The other constraint, the circle constraint, I'm just going to represent with an assertion. And I'm going to say that a legal execution path of this program has to satisfy the assertion. And so I want to reason about the min and max values under that constraint. And here on the right, I've drawn what the graph would look like for this program, which is essentially just saying how each variable was computed, what other variable was computed from. Okay, so the way we're going to solve this by message passing is essentially we're going to end up passing messages in that graph. However, I'm going to give you a program which does the message passing. I'm not going to assume that we're constructing the graph in memory and passing messages that way. This is just sort of a helpful mental tool. Okay, so just as with AD, the first step in doing this message passing transformation will be to ensure that every variable is defined and used once on every execution path. So I'm going to make this edge program as I did before. Now, if you look on the left, there's only one variable that violates that condition, and that's y. So it's used twice. And so we know the fix for that. I showed it before. You just introduce this duplication operator, and now every variable is used once. And a nice property of that is that now that graph that I showed before can be rewritten this way so that it has the same sort of topological structure. However, now every variable in the program is an edge in the graph. And the nodes of the graph are actually the operations in the program. So that they're the operations that relate variables to each other. And this is in the machine learning literature. This is actually called a Forney factor graph, which is simply a simplified factor graph where you don't need the variable nodes because every variable is defined and used once, so they're just edges. So it gives you a nice compact way. So having made the edge program, I now make a transformation into a message program, and this transformation resembles the backward pass of AD. The only difference is that now I'm going to have forward messages as well. I'm not going to only have backward messages. And
Tom,
yes.
Is this program supposed to be the one that you showed before?
Which one?
Any previous slide? Yeah.
Is it not? Wait, did I mess up? It is, right?
Go back with the square and the parabola.
This is the same program as that. It should be.
No, we one before.
Yes. Is it not the same program?
Before.
Before.
Yeah.
So you're looking for x and y, which means you have two inputs to search for.
Yeah, but what I've done is
One's
I've written the program in such a way that x is the only input because y is just defined to be x squared. So I cheated a bit. I could have made an assertion
You
that.
mentioned that you were cheating.
Yeah, so I could have written this as two assertions on x and y, but the problem is then the graph gets a one node bigger, and I didn't want that. But you could do it that way, and you'd get the same results.
You could have changed the problem statement saying find x such that.
Yes. So think of it that way. Yeah, you can see from this picture that clearly x is the only input to the program, right? Okay, so back to the message program. So I'm not showing the full message program. I'm just showing the essential bits. essentially, so here what we're doing is I'm not going to reverse the order the way I did with AD, and I'll explain why that is. But essentially now it's just going to be line by line transformation. So the first line, so what I'm doing is I'm making a new set of variables which are going to be f and b variables, which just correspond to the two messages along each edge, right? So remember, every variable in this program is an edge, and every variable in this program is a message, and there's always two messages on every edge. So it's just an f and a b.
And what is the data type of yf?
It's an interval, so it's two numbers, a min and a max. Yeah. Whereas on the left, it was just a real number. And that's why you have these funny operations like intersection and so on. In fact, you can see it at the bottom, right? So this assertion turned into ZB equals the interval 1, 1. It has to be the number 1, yes?
So there's an application of square root. Where did it come from?
I will explain that on the next slide. That's a good observation. Let's start with the easy cases first. So in this case, the forward message to y is just the square of the forward message to x, so that one's easy. There's also going to be a backward message, which I omitted.
Sorry, easy
yeah.
means the square of an interval is max minus max squared to max squared?
It's not that simple. So think of it as the smallest interval which contains all the squares of the numbers in the input interval. Which, right? That always exists, but the formula may be a bit complicated. I'll give an example of how to derive one of those on the next slide.
But minus max squared to max squared is probably it. Oh, I assumed max was positive.
No.
Sorry. Yeah.
No. So it depends a lot on what the signs, like does it cross 0 and so on. So there's all these special cases to worry about. But it's very handy if you can just abbreviate it as square. Okay, so the duplication operator, so what happens there is that the forward message to y1 is just the forward message into y intersected with the backward message on y2b. So if you look at the graph, it's easiest to see it that way. So the message I'm sending forward along y1 is going to combine the message from y and from y2. And what combine means in the case of intervals is intersection. And then there's a similar line for sending the message to y2. And there's also a message yb back to b, which I'm not showing.
So, Tom?
Yeah.
So when you do this transformation, when you look at these new variables which are intervals, you're assuming that the domain is some lattice.
I am not assuming that, no. So in abstract interpretation, you'd have a bunch of constraints about how abstractions have to be consistent with the original concrete values and so on. None of that happens in general message passing. So the guarantees of convergence and so on that you get in abstract interpretation do not generally apply.
But when you said it was an interval, you meant it was an interval, not
Yes.
a union of intervals, just an interval.
Just an interval, yes. Yes. Yeah, well, I guess another potentially confusing thing is that in one of the original papers on abstract interpretation, they actually used interval propagation as the example. But I'm doing it in a different way than they did in that paper. See if you can spot how it's different. Okay, so going to the third line, here we have just two variables being related by a factor, and that's the easiest case. And in that case, we just have a forward message down and a backward message up. And the forward message down intuitively is taking the interval containing all squares of the input number, right? And the backward message, if you think about it, has to be all numbers which when squared, like what is the largest set of numbers which when squared would fall into the output interval, right? And I'll explain that in the next slide. But it's essentially, if I have a constraint on the square, what do I know about the input? Just think of it that way. And then here we have the sum, and that turns into, again, messages. So there's a backward message to y2 and a backward message to yy. There'll also be a forward message to z, which I'm not showing. Okay, so the important thing to remember here is that it's just like AD, right? I can draw little graphs for each of these steps of the program, and I'm just sending messages to variables in those graphs. The only difference is I'm not reversing the order of the program. Okay, so how does that square root thing work? So as I said, if I have this constraint that yy is y1 squared, and I know something about yy, I have a backward message from yy, how do I figure out what I know about y1, right? And so a useful way to think about, so one thing that's funny about this square root operator is it has 2 arguments, which already seems weird, right? Why does it have 2 arguments? And that's because it's doing this, it's shorthand for this projection operation that I'm writing here. And to think about why that projection is necessary, I'm going to go through a concrete example. So let's suppose YYB, which is what we know about YY, going from the bottom, is the interval 2, 4. So what are the possible square roots? Well, it's actually a union of 2 separate intervals, right? So the square root is either a number between 1 and 2, but it could also be a number between -2 and -1, right? Meaning numbers which when squared would land in that interval. So this is the set of all numbers which when squared would land in the interval 2, 4. But the problem is that that's not a legal message type, that union of 2 intervals. Now I could do something so I could make an over-approximation and say, well, that's the interval -2 to 2. But the problem is if you do that, you lose a lot of precision. And so, I mean, you still get valid bounds, but you'll get very loose bounds. So here's a better way to do it. So what we're going to do is we're going to look at the message from the other direction. We're going to use what we already know about y1. So suppose the message into y1 from the other direction is the interval 0, 10. So in other words, I already know y1 is positive. So what you do there is you intersect that message with this fancy square root object. And what that does is that kills off one of those intervals. And now you just have the interval 1, 2. And this project, when I say project, I mean just find the interval that contains everything. So the thing on the inside doesn't have to be an interval, but the output has to be an interval. And so we get the interval 1, 2, which is the most precise result in this case. If I had done it the other way, if I had done it the naive way, if I had first forced the complicated square root set to be projected into an interval, and then intersect, I'd get 1, 2, 0, 2, which is obviously looser. So that's why the square root operation takes the message in the other direction as input, because you can think of it as I'm temporarily working with a higher precision. I'm using a more flexible representation of messages internally so that I can give a more accurate message out. Okay, so what are the actual results if you run this program? So if you start with all intervals at -infinity to infinity, and then you iterate this program to convergence, then what you end up getting is that x is in the interval -1 to 1, which does contain the 2 solutions. However, it's an overestimate. In fact, it doesn't even tightly bound the 2 solutions. It's bigger than that. However, what we can do from here is we can apply subdivision. So we can say we can take a piece of that known interval where x has to live and run the algorithm again. So for example, if we take the chunk, take the interval from 0.1 to 1, and then we iterate the algorithm, we find that it then converges to a point. So it converges to exactly that solution in the positive quadrant. And if we started it with a negative interval, it would converge to a point, which is the negative solution. And in fact, this subdivision technique, it's also called decimation in the literature, is a generally useful thing for message passing algorithms.
What happens if you chose an interval that didn't contain a solution, like 0.5 to 0.5, -0.5?
Then what would happen is the interval, you'd eventually get an empty interval. And when you run the iteration, all the intervals then become empty. So nothing's possible. It's impossible.
Is there some starting point where it would compute the interval minus 0.786 to plus 0.786?
I'm not sure. Probably if you initialized it with that, I think it would. Because I'm pretty sure the algorithm is guaranteed to never increase the input interval. So yeah, so if you initialize it, it would definitely give you that as the answer. Yeah.
So what are the formal guarantees on the relationship between the message passing program and the program you derived it from? To give you an example from this original interval propagation paper, so basically there's this soundness theorem that says range you compute is a superset of all the ranges that the program can actually go through. Do you have something similar here?
Yeah, I believe that's true in this particular case. All right, I don't want to get bogged down with the properties of interval constraint propagation because that's a very, very specific algorithm. And I really just want to talk about the general class of message passing algorithms.
But is it something that you strive for, that there is a formal relationship between the message passing program and the original program that it kind of holistic?
In the literature, no. So compared to, for example, papers on abstract interpretation, where they do strive very hard to show that there's a connection, if you look at a paper on message passing from machine learning, you will almost never find stuff like that.
And for you, is it important?
Well, you can show me that it's important. I'm willing to be convinced that it's important.
But you're not willing to answer the question.
I have not used it myself. I've done lots of message passing algorithms and I've never done that. So, there's some neat things you can do with this interval propagation program. So the way I derived it so far was, I just naively converted all of the statements in the edge program to get these message statements, and then I wrapped the whole thing with an until convergence loop. Yes?
Following the flow of the graph, the backwards variables seem to appear in the forwards order. So are they really backwards variables? Because YB appears after XB. So it seems like it's another version of a forward variable, another version of a forward sweep.
Well, I'm not sure about that. Well, the order here doesn't matter. Let's think of it that way, because it's just a convergence loop. So, and no variable is assigned more than once. So essentially, the order is irrelevant here. The important thing is just that every edge in the original graph just turned into 2, and I just happened to name them forward and backward. Is that good enough?
Sure.
Okay.
Yeah.
So starting from this naive program where I just translated every line and just wrapped it with an until convergence, you can do a variety of optimizations to make it more efficient. So one of those optimizations would be to hoist things out of the convergence loop, because you know that they don't change. So for example, there are lines you can hoist at the beginning, like this ZB equals 1, 1 doesn't depend on anything in the convergence loop, so you can just hoist it out. And you can just recursively keep doing that. Whenever you find a line that doesn't depend on anything in the convergence loop, you hoist it out. And then same thing for the end. You can put statements at the end where nothing in the convergence loop depends on those statements. And so those go to the end. And so so this is actually a very general property of message passing programs, is that you'll have a graph which has some sort of loopy core, and then you'll have chains going into it. And so the general structure of the algorithm will be, you sort of pass messages into this loopy core, you iterate the loopy core, and then you pass messages out of the loopy core. And there's a machine learning language called Stan where the user actually has to explicitly say what things are done before the iteration and then what things are done after. Here, we're sort of driving it automatically just by examining properties of the output program. So there's some other simplifications you can do just based on looking at the message dependencies. So for example, if you notice that the forward messages don't depend on the backward messages, then by applying the optimization that I just described of hoisting things out of the loop, what you'll find is that nothing remains in the loop, right? And so then the algorithm is the resulting program is non-iterative. And another optimization would be that if the forward messages only include a single state, so they're not intervals but they're just points, then you will only ever need to explore one execution path, right? Because you'll always know which branch is taken on any sort of fork. And so you can optimize that case as well. And it turns out that to get AutoDiff, you essentially just exploit both of those two properties, that the forward messages don't depend on the backward message. The forward messages are always just points. They're just exact values, and so you only need to explore one execution path. And so essentially, even though this looked like this message passing program was more complicated than AutoDiff, if you perform these optimizations exploiting these properties, you will actually just get the AutoDiff program out, because essentially it'll reverse the control flow of the program based on the dependencies. Okay, so I showed one example of a message processing program. There are other message passing programs, message passing algorithms, and a lot of them center around probabilistic programming. Now, I like to draw an analogy between probabilistic programming and AD, in the sense that just as programs are the new formulas for AD, probabilistic programs are the new Bayesian networks for probabilistic machine learning. So instead of thinking of a problem as a Bayesian network, you should pretty much always think about it as a program, because you get the same benefits. It's not only a more compact input, but after you transform it to do inference, it has the same size. So it's also compact in terms of representing inference. Okay, so one well-known message passing algorithm for probabilistic programs is Loopy belief propagation. And if you actually look at what the difference is between that and the interval constraint propagation example, it's actually exactly the same. So all of the transformations that I made for the interval case are the same transformations you'd make for Loopy belief propagation. The only difference is that the message type is different. Instead of the message type being 2 being an interval, the message type is now a distribution, which can be parameterized in a variety of different ways. So if it's a discrete variable, you would just have a set of numbers representing the distribution. If it's a Gaussian, you'd have a mean and variance, and so on. But other than that data type change, it's the same structure of algorithm. And Loopy belief propagation has the nice property that if you apply it to a Markov chain or a parse tree model or so on, you get the forward-backward summations. So unlike AD, which gave you the backward summation, if you gave it already the forward summation, Loopy belief propagation gives you both just from the original model. And if you want to do approximation, you can do expectation propagation, which essentially adds projection steps to Loopy belief propagation, similar to the projection step that I showed for square root. So the way that EP adds these projection steps is very much analogous to that square root projection step. And that's how you can get approximations within message passing. And finally, gradient descent. So the way you can get gradient descent with message passing, and I don't mean AD, I mean the actual gradient descent algorithm, is you put the parameter into your model, and what this parameter does is it sends its current value out to the functions it's connected to the nodes it's connected to, and it receives back a gradient. And after it receives back a gradient, it can then take a step and then sends a new value out. So in fact, you can implement gradient descent as a message passing algorithm. And what also is an interesting thing that turns out is that if you take the expectation propagation messages and you apply them in the case where the input is a point mass, so in other words, theta is known, it has a single value, and then you ask what is the EP message back to theta, it turns out that's the gradient. So if you implemented expectation propagation, you essentially have already implemented gradient descent in this, but by using this special case. And what's nice about this is that not all of the variables in the model, for example, have to be doing this gradient descent update. So some of them could be doing just full EP, they could be doing belief propagation, and others could be doing gradient descent. And they can all be done in the same iteration loop. And Gibbs sampling can also be explained as message passing as well. But I'll skip that unless people want to see that. That concludes my talk. Thank you.